Okay, so we've covered a couple parts on the periodic table. We have covered how they came up with the periodic table, just based on properties. We've learned why it is that way. Okay? It's about the electrons and how they're arranged. Now, we're going to talk about some of the patterns you can see on the table. Okay? Trends in specific properties. Okay? Because Mendeleev could predict what they were going to be like because there was a pattern to the properties. We're going to investigate some of those patterns. That'll tell us, which we can use later to predict how these chemicals are going to react with each other. That's what we're trying to go to. We're trying to do chemistry. What happens when you put this and this together? Okay? Once we understand where the electrons are at, then we can start talking about what happens when you put chemicals together. Okay, so we're not going to study all the patterns. There's 4 patterns we're going to investigate. So there's 4 patterns we're going to investigate. The first pattern we're going to investigate is atomic size. Sometimes, instead of saying atomic size, they'll say atomic radius. But those are both just ways of talking about what about the atom. What are we measuring? How big they are. Some atoms are bigger than others. And there's a pattern to their sizes. Hey, ionization energy. So what the heck is this? Well, just from the name, ionization energy, what do you think you're measuring? Energy to ionize. Does that make sense? Just a matter of what is ionizing. Okay. Ionizing, in this case, is taking off an electron. How much energy to take off an electron? Now, it's a lot like the photoelectric effect from last chapter, except the photoelectric effect was when it was on metals. We actually measure ionization energy for gases. So if you got a metal and you want to know its ionization energy, first you melt it, then you boil it, then you measure how much energy to knock the electron off. So we're comparing all the atoms the same way. They're all in the same situation, because it wouldn't be fair to compare a solid to a gas. So we get everything to a gas, and then we test ionization energy. Because then the atoms are separate from each other. So it's just what that atom's going to do, not how it interacts with another atom. Electronegativity. Is the next trend. And electronegativity is how hard you attract the electron in your neighbor. Not how hard you attract your own electron, how hard you pull on your neighbor's electron. So you can't test it until you have a compound. Once you make a compound, you can measure how hard this atom is pulling on that atom's electron. I kind of think of it like greed. How greedy are they? Got my electrons, I want yours too. Okay? And once we make ions, what are their sizes like? How big the ions are once you change the number of electrons. Because changing the number of electrons will change the size of your atom. What these all have in common is they're all about attraction. Always about attraction of the nucleus for electrons. It's all about opposites attract. If you've got a strong attraction, it's going to pull those electrons in really close, and your size will be small. If you've got a strong attraction, it's going to be hard to remove the electron. It'll take a lot of energy. If you've got a weak attraction, it'll be easy to remove the electron, and it won't take much energy. Okay? If you pull on your neighbor's electron hard, what's going to pull on your neighbor's electron is your nucleus. Your nucleus is going to pull on your neighbor's electron. Opposites attract. Okay? And ionic size for the same reason. That nucleus is going to pull on the electrons. If it pulls a lot, the ion gets small. If it pulls just a little, the ion gets big. Because the more you pull, the closer it's going to be. Seem reasonable? These are all just about attraction between nucleus and electron. Opposites attract. Okay? What we're going to look for about those things, we're going to look for periodic trends. We're going to look for periodic trends, which means we're going to look in periods. So first period, we'll look for something. The second, no, not those kind of periods. We're going to look what happens as you go across a period. What happens to the size of atoms as you go across a period? What happens to the ionization energy as you go across a period? What happens to ionization or electronegativity as you go across the period? How do things change as you go across a period that affects that attraction? Okay. And we're going to look for group trends. How those things vary as you go down a group. Groups we always compare from top to bottom. Periods we always compare left to right. We say across, we mean left to right because we read in English, not Hebrew, not Arabic, not Japanese. They all read in different directions. So first we're going to learn what the trends are. Actually, not first. We're going to explain what the trends are, but we're going to answer why questions. Why does the atomic radius change as you go across the period? Why does the atomic radius change as you go down a group? What's changing that changes the radius? Okay. So why those things vary? So these questions are going to be about the atoms. What's happening in that atom that makes this different? It's going to be about how the electrons are arranged, because it's electrons that cause the properties. Fact is, we're going to start not with what the trends are, but the why. We're going to figure out the why first. We know enough to figure out the why. And it's got to do with electron configurations and how they change on the periodic table. And it's got to do with the positive nucleus pulls on the electrons. All of these behaviors, the two sizes, ionization energy and electronegativity, are all about how hard that nucleus pulls on a negative electron. So so we're answering why questions. We got to talk about why that pull changes. Okay. And there's different reasons. There's one reason for the periodic trend. There's one reason for the group trend. They're not the same. So the periodic trend. So as you go across the period, what changes? Let's just look at period number 2. Okay, look at period number 2. What changes as I go across the period? Well, I get this lithium has 3 protons and 3 electrons. Neon has 10 protons and 10 electrons. Okay. So neon's being pulled with 3 protons, or lithium's being pulled with 3 protons, neon's being pulled with 10 protons. Okay. As you go across the row, the charge on the nucleus gets bigger. Because as you go across the row, you add 1 more proton every time as you go. So you get more and more positive as you go across the row. Say, well, you're also adding more electrons. But when we're adding the electrons, when we add the electrons, they're going to go into the second energy level here, right? 2s1. Second energy level here, 2s2. 2p's, right? These are the 2p's. So all those electrons are going in the same energy level. So they have more protons, so there's a bigger pull. But that bigger pull is affecting the same energy level. So that means the outer electrons are pulled stronger. They're pulled more because you got more positive charges to go across. Lithium pulls on the electrons with 3 protons. Neon pulls on the electrons with 10 protons. Neon's going to pull better than lithium. And it's going to be that way on every period because they just keep going up by atomic number. Every row is going to be that way. Less attracted on the left side, more attracted on the right side. Okay. So here we are talking about it. This would be what a Bohr model for lithium would look like, right? I had more electrons, it's pulled more because I got more protons. So that 10 protons are going to pull better than 3 protons. And on the next row, 11 protons won't pull nearly as well as 18 protons. It's going to happen on every row all the way across. So the reason for our periodic trends is going to be positive charge on the nucleus. The group trends. The reason behind the group trends. So if I go down this group, thinking about the electrons, what changes? Because every one of these is going to end in S1, but hydrogen is going to be 1s1, lithium is going to be 2s1, sodium is going to be 3s1. So every time you go down a row, every time you go down a group, you add an energy level. You add a layer of electrons. And adding that layer makes those new electrons less attracted. Oh. How does adding a layer of electrons make it less attracted? Well, it happens because of something called shielding. Outer one's not as attractive. Hey, happens because of shielding. So, what's the working theory behind a shield? How does it protect you? Well, when somebody is swinging an axe at your head, you're hoping the shield gets in the way. That's basically what happened. It gets in the way. Your plan is, I'm going to get this in the way of whatever you're doing, right? That's what they mean here. The electrons get in the way. Because this is a potassium atom. I can tell because it's got 4 energy levels and 1 electron. 4th energy level, 1 electron is potassium. Okay? But in order for this electron to be attracted to that nucleus, there's all these other electrons. Each one of those rings is a bunch of electrons. So I've got negative charges between my electron and the nucleus. The inside layers get in the way. And it says look through. It's not really look. They don't have eyes. Shouldn't be anthropomorphizing. Okay. So in order for the negative electron to be attracted to the positive nucleus, I've got negative charges here, so they're going to get in the way. They're going to repel that a little bit, and that's going to make that outside electron less attracted. Now, if I go to calcium, the next atom, I add another electron out here, but it's still in the fourth energy level, so I don't affect the shielding. So as I go across a period, I'm just going to keep adding to that outside layer, and my shielding is going to stay the same. And that's why the positive charge is all we worry about when we go across. The shielding stays the same. All that's changing is the positive charge. So that's why on a period trend, we only have to worry about nuclear charge. On a group trend, we have to worry about energy levels. So in the same energy level, in the same period, shielding's the same. Making sense? To me, it's like you go home. Hey, Mom, look at this picture I drew. It says, lovely. Let me put it on the fridge. It's a magnet. Holds that on the fridge. Come back the next day with a lovely picture. Say, let me put that on the fridge. Takes the magnet. Now it's holding two papers. The more papers you put between the magnet and that fridge, the less attractive the magnet is. The more electrons I put between the outside and the nucleus, the less attractive the electron is. So, a hydrogen atom, one energy level, one electron. It has no shielding. It's going to feel the full effect of that positive charge because there's nothing in the way. But as the energy levels change, the shielding changes. So this is hydrogen. If I go to lithium, the next one, lithium, it's got one electron on the outside, but that one electron has electrons between it and the nucleus. So that electron's going to come off, that would be a little less attracted. And then I go to sodium, now it's got two shields. Two inner layers blocking that nucleus. Just like putting more papers behind the magnet, it makes it less attracted. And then potassium, the one we saw, had three shields. Because it's in the fourth energy level, those three other energy levels are down lower. So the lower down the group, more energy levels, more shielding, less attracted. Okay. So just check to make sure we're all in the same place. Three of these are right, one of them is wrong. Which one's wrong? Okay. What did you choose? Okay. Does nuclear charge increase as you go across a period? Well, go across the period, nuclear charge is protons. The number of protons increase? Yeah. So that can't be the answer. Does nuclear charge increase as you go down a group? Well, this has one proton, that has 3, that has 11. The nuclear charge increases down a group, so it's not that one. Does shielding increase as you go down a group? Because I have no layers, 1 layer inside, 2 layers inside. So shielding increases the further down the group you go. So that leaves us with shielding increases as you go across the period. Shielding is not going to change because this is 2s, second energy level. This is 2p, second energy level, all with one shield. Shielding stays the same across the period. It changes as you go down groups. So we got two effects. One makes the electron more attracted, nuclear charge. One makes the electron less attracted, shielding. And they don't change at the same time, so it's going to build patterns of when things do change. Okay? This is why our patterns are going to happen, is because we have two opposite effects that change in different places. Okay? So if you've got this, I would summarize today's lessons with this. Be handy to write down. Our coloring from Friday. Okay. So, you got that on the front side. We've got them all colored. You studied that one. So down that one, you got the one where you got two sides colored. If you go across the row, the electron is going to be more attracted by a larger nuclear charge, always. As you go down a group, it's going to be less attracted because of more energy levels. More energy levels are going to shield. And that's where I wanted to stop for today.